Hi guys, today we're going to do Chapter 10, Alcohols, and I'll bundle in Chapter 11 with this because it's also alcohol chemistry. So, here we go. Chapter 10 and 11 is essentially alcohol and alcohol chemistry, right? So the stuff that alcohol does. Alrighty, so what do we have for these chapters? For Chapter 10, we have a little bit of nomenclature, which is relatively easy. Nomenclature. We have alkoxides and phenoxides. And what else do we have? We have synthesis. So a brief review of synthesis because we already did synthesis of alcohols when we did addition reactions. We know 3 different ways to do it, or 3 different simple ways. Then we have synthesis. So this would be synthesis of alcohols. And this will be synthesis of vis diols. Also a review. Vicinal diols because we've already done this, so we know a couple of methods for that. A new topic for this chapter, and a big important topic in organic chemistry in general, is Grignards, or Grignard chemistry. Big important. And then also, which is new for oxidation, which we haven't really covered yet, or for alcohols, which is oxidation and reduction chemistry. Alrighty. And I guess if we have time, we'll throw in a little thiols. They do the same thing that alcohols do. They're not terribly important in organic chemistry, but you will see them in biochem for sure, so couldn't hurt to mention them and say, oh, by the way, they do some of the same stuff. So let's talk about nomenclature first, get that out of the way, go down a little bit more. Nomenclature of the alcohols. It's really easy to do, right? You do the same thing to name like alkyl halides, only instead of putting it a prefix like a 3-fluoro or 2-bromo, you drop the E and add OL for the alcohol name, and it's a suffix rather than a prefix, right? So if I had something like this, you still count the longest chain, and then you still count so that the highest priority group is at the lowest number. So 1, 2, 3. So at the 2 position we have a methyl. At the 1 position we have an alcohol. There are 3 carbons in the longest chain, so it would be propane. Drop the E and add OL. Because we're using that UPAC system, we want to specify explicitly propan-1-ol, or you could say propanol. A UPAC accepts either one. Something like this, simple alcohol at the 1, 2, 3, 4 position. Butane for 4 carbons, drop the E and add OL, specify the position, butan 2-ol. Easy peasy. Okay, if we have multiple functional groups, like an alkene or an alkyne, we touched on this last chapter. Suppose we had something like this. Right? We could count 2 possible ways, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. You should always count such that the highest priority group is at the lowest number, and so it should be 1, 2, 3, 4, 5, even though counting the other way would put the alkene at position 1. So at the 2 position we have all, at the 4 position we have an ene. In this case we don't have to worry about cis and trans, and we don't have to worry about E and Z either. So this would be 5 carbons is pent. Since there's a double bond at the 4 position, it'll be pent 4-ene. And at the 2 position, we have alcohol, so 2-ol. Right? Alcohol's higher priority group, so it should be ene and then ol. I should probably look this up, but I don't remember if it's alphabetical, E versus O, or if it's priority, OL comes last. I think it's alphabetical actually, so E comes before O, so that's why it's pent 4-ene 2-ol rather than pent 2-ol 4-ene. But I could be mistaken on that. Either way, I don't really care about that level of detail. I just care that you can recognize that the highest priority group has to go to the lowest position, count the chain properly, and then specify where the groups go. I'm not terribly interested in nomenclature at this point because there's a lot more important things like synthesis reactions and mechanisms that we get to do. Sometimes the alcohol group is not the highest priority group. So an example that I gave in class looks like this. Right? Now we count the alcohol loses in priority to the carboxylic acid functional group. So we should count 1, 2, 3, 4. And so at the 4 position we have the alcohol, but because it's not highest priority anymore, it changes its name. It no longer becomes an all, it becomes hydroxy. Excuse me. So at the 4 position we have 4 hydroxy, and then we name the rest of the molecule, which we butane. And then we haven't learned how to name carboxylic acids yet. We will at the end of OChem 2. So for now, I'll just tell you the suffix for carboxylic acid is just oic acid. You drop the E and add oic acid. So 4-hydroxybutanoic acid. If you name this the common system, it would be alpha, beta, gamma. So this would be gamma. Oops, G-A-M. I have an eraser when I need to scribble things out. Gamma hydroxy butanoic acid, which is sometimes referred to as GHB. And if you know what that is, you're a creeper. Alright, next, phenols. Phenol is a grandfathered name from IUPAC. So phenol is essentially 1-hydroxybenzene, right? Or benzyl, not benzyl alcohol, but benz alcohol. So this is a grandfather name through IUPAC, and it's acceptable to say phenol is that. So if I start tacking things onto my phenol molecule, like a chlorine at maybe this position, we count the highest priority group, which is the alcohol, so it would be 1, 2, 3. So we would say this is 3-chlorophenol, right? If we put it at the 4 position, it would be 4-chloro. If we put it here, it would be the same thing as putting it back at the 3 position, because you could just flip the molecule over, and then you would count 1, 2, 3 this way. If I count 1, 2, 3, and then if I put something here, like a bromo, then it would be 3-chloro, 4-bromo. Excuse me, 4-bromo, 3-chloro, because B comes 4C. So that does apply. And phenols do a little bit different chemistry than alcohols do. So we will look at those in a minute. And one more example of alcohols. If I had a diol, oops, I could have something like, give my pen function back. We can have something like this. All right, 3 carbons along this chain, 1, 2, 3, or 1, 2, 3, 1, 2, 3. And so at the 1 position I have an alcohol, at the 2 position I have an alcohol. So it would be propane because it's 3-carbon chain. Drop the E and add all, but because there's 2 of them, we have to say where they're at the 1 and the 2 position. Diol, so propane 1,2-diol. This is also called the glycol. That's kind of the common name for diols, or especially the 2 and 3 carbon chains, glycols, like ethylene glycol that you see to put in your car for antifreeze. Usually you see antifreeze is made of propylene glycol or ethylene glycol. This is essentially just what it is. It's that mixed with water, usually about 50-50 mix. Just changes the physical properties of the water by a little bit. Okay, so let's look at alkoxides, right? Some actual chemistry with alcohols. Alkoxides, right? What is an alkoxide? If I take an alcohol and I deprotonate it, for example, by adding sodium metal, right? Why do I add sodium metal? Because sodium metal can donate an electron to the hydrogen, and the hydrogen will interact with another molecule of the alcohol, and it will give off hydrogen gas. But more importantly, it will give me this, which is the alkoxide. Right, the alkoxide is a relatively good base, right? We've been using them for a while to do our elimination chemistry now. But depending on the situation, you can also use them as a nucleophile. So if I take something like my favorite alcohol, ethanol, and I add sodium or sodium hydride, I can get ethoxide. And I can use ethoxide to do nucleophilic chemistry if I want. I can go off and I can attack some electrophilic target, right? Like alkyl halides, for example. That would be a Williamson ether synthesis. It's chapter 13 in your textbook, but you'll learn that the early part of next semester. Turns out you can do the same thing with phenols. So if you take a phenol and you add now with phenols, hydroxide, like sodium hydroxide, is a strong enough base to make this happen. Why? Well, the pKa of a phenol is about 10, right? For phenol specifically it's 10, but for decorated phenols it would be about The pK of an alcohol, if you recall from a couple lectures ago, is about 14 to 16, right? It's much higher. Remember, the lower the pKa, the stronger the acid. So this is a stronger acid. But why? Well, it's a stronger acid because after the phenol gets deprotonated, this guy is resonance stabilized. And you should be able to draw 3 more resonance contributors. Go ahead and pause the video and try and do it with this structure. I'll give you a hint. The first step is this. Okay? So because of this resonance stabilization, it means it's a more stable base, which means it's a better acid. Here, no resonance possible. And so that's what makes all the difference between a phenol and an alkoxide in terms of its acidity. So again, we can use phenols as bases. We can even use them as really, really weak acids, but it's uncommon. Or we can use them as nucleophiles. But they're not great nucleophiles because they got this big benzene ring kind of tagging along with them. So a couple other things you can do with phenols. We'll see more phenol chemistry later on in Chem 2. All right, let's do a quick review of how we can make alcohols. So alcohol synthesis, right? So we know 3 ways. I'm going to go ahead and pause the video real quick right now. Try and think of those 3 ways. They're addition reactions from Chapter 8. Alright, hopefully you came up with this. One way is hydration. So an alkene plus aqueous acid will give you the Markovnikov product of the alcohol. Right, so you've hydrated the molecule. The other way is the no rearrangement possible oxymercuration demercuration, so HgOAC2, followed by sodium borohydride. That also gives you the Markovnikov addition. So this one's Markovnikov, this one's Markovnikov. And if you want to make the anti-Markovnikov molecule, we also know how to do that. And the third method was hydroboration oxidation, BH3 with some type of organic solvent like THF, followed by oxidation of peroxide and aqueous base to give us the anti-Markovnikov product. Give us this. Okay, so those are the 3 ways that we know. For vis diols, it's a little bit different. Review. How do we make of synthesis of vicinal, V-I-C-I-N-A-L, diols? Right? How do we make vicinal diols? We know 3 ways. Go ahead and pause the video now and try and think of those 3 ways. If you have to write stuff down, that's fine. But ideally, it should be in your head. Okay, so hopefully you unpause the video and you came up with this. For a syn diol, where both alcohols are on the same side relative to each other, we know 2 ways. We can use osmium tetroxide, or we can follow by peroxide to oxidize it off. And that will give us a structure that looks like this. Right, a syn diol. We also know that we can use our very variable friend, KMnO4, potassium permanganate, but it necessarily has to be cold and it has to be dilute, right? That's very important. And I believe often it can be basic as well, so OH minus is usually there too. That will also give us the syn vis diol. And we know one way to make an antidiol. Unfortunately, this is not 1 step, it's 2 steps, and hopefully you came up with this method as well. This is to epoxidate with like MCPBA or MMPP, followed by popping open the 3-membered ring either with aqueous acid, you can do acid catalyzed, or with aqueous base, you can do base catalyzed. And this will give us the transdiol anti-addition. So those are things we already know and you already know the mechanisms for. If you don't know those, if you don't remember them, go back and look at your addition reactions from Chapter 8. Okay. Why is this important? Well, it's important because we can take diols and we can oxidize them to carbonyls. If we want to oxidize this one, right, we can oxidize the carbonyls. So oxidation reduction chemistry is one of the things that alcohols can do that the alkyl halides, the alkenes, I mean alkenes can do a little bit, alkynes can do a little bit, but alcohols can really do a lot, right? It really opens the door to a lot more complex functional groups like aldehydes, ketones, esters, carboxylic acids, acyl halides, and all the other fun derivatives we can make. So let's take a look at the things oxygen can do. Oxidation, reduction. Alright, so you remember from Gen Chem, I'm sure, that oxidation reduction is like an electron goes over here, and so this guy gets reduced, and then this guy gets oxidized because he lost an electron, and blah, 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 blah. That's way too complex. We're not going to do any of that. That's too hard. You got to pay attention to electrons and stuff. Let's make it easier, right? In organic chemistry, we say that oxidation is a gain of atoms on the molecule that are more electronegative than carbon, right? Again, this is organic chemistry, so we care about what carbon is up to. I don't know why that, whatever, more electronegative than carbon. Okay. Another way to put this is to say, or you can consider oxidation to be a loss of hydrogens. Right, so you have two ways to look at oxidation. You can look at the atoms that are more electronegative than carbon, like bromine and chlorine, or oxygen even. Or you can look at the hydrogens and say, did carbon lose hydrogens, or did it gain hydrogens? Two sides of the coin. And therefore reduction will be a loss of atoms that are more electronegative than carbon. Electronegative than carbon. Or, if we want to pay attention to what the hydrogens are doing, reduction would just be a gain in the hydrogen count. Right? So last chapter when we learned hydrogenation reactions, we take an alkene and we hydrogenate it with hydrogen and platinum or Raney nickel or palladium or something like that, and we get the cis addition. Technically, that was a reduction because we've gained hydrogens on the molecule. I didn't say it that way because I didn't want to throw in all this nomenclature and language and concepts of oxidation and reduction chemistry, but that's really what it is. It is a reduction, right? It's a reduction through the addition of hydrogen in this case. All right, so let's take a look at some examples. I want you to tell me if you think it's an oxidation or reduction or neither. If I take ethene, the simplest alkene, and I hydrate it to make an alcohol. Is this an oxidation or a reduction? Go ahead and pause the video, ponder about, stroke your chin, and then unpause it and come up with an answer. Hopefully you've unpaused it and you said that this is neither. Why is this neither, right? Well, we've added a hydrogen, so that would be a reduction, but we've also added an atom more electronegative than carbon, oxygen. So we basically took one step down towards reduction and then one step up towards oxidation. So 2 steps forward and 2 steps back. So don't ask me why I just sang Paula Abdul. So they cancel each other out, right? But Jay, what about this hydrogen over here? The one that's bonded to the oxygen. That also got added as well. That's true, it did get added. However, what we care about in organic chemistry is what the carbon is up to, right? From carbon's point of view, he gained 1 oxygen bond, this one gained 1 hydrogen bond, and so it's a wash. So this would be neither. What if we take the same alkene and we do bromination, Br2 and carbon tetrachloride? Right? Go ahead, pause the video, predict the product, and then tell me if it's an oxidation or reduction. Hopefully after pausing, you discovered that the product looks like this. And I'm just omitting stereochemistry out of laziness, but you need to know stereochemistry, right? Anti-addition. And this is carbon with too many bonds, that's what that is. And this is an oxidation. Why is it an oxidation? This carbon has gained an atom that is more electronegative than carbon, bromine, and so has this one. So we just went 2 steps forward in the oxidation category. And like I said a second ago, if I do something like this, the product would be ethane, and this would be a reduction. right? So that's a very standard type of question you'll see from me, from the ACS exam, or whatever. Alright, so why is all this important? Why are we talking about this crap? Well, the reason we're talking about it is because there's lots of different levels that you can play with when you have molecules, right? So let's start with the scale. Like, this is how I think of the oxidation reduction scale. I say the most reduced form of carbon is methane, where you have the most amount of hydrogens attached to the molecule you can. So this is the most reduced. I can elevate I say elevate because I always think oxidation is up in the sky and reduction is down under the ground. It doesn't make any sense that way, it's just how I visualize it. But if I increase my oxidation state by 1, right, I increase the number of carbon to electronegative element bonds, or I decrease the number of carbon-hydrogen bonds, whichever ones I want to focus on, either way, I go up in oxidation, at least up to my point of view. I go slightly more oxidized, so I get something like this. If I oxidize again, I go from 4 hydrogens to 3 hydrogens to 2 hydrogens. Or I go from 0 oxygens to 1 oxygen to 2 oxygens. Now, I'm counting this as 2 oxygens because there's 2 carbon-oxygen bonds. I could also write it as this. This is called a gem diol. It's a real molecule, not terribly stable, but it does exist. Right? These are the same oxidation level. Right? So I could, either one of these doesn't matter. If I continue to oxidize my molecule, I go from 4 hydrogens to 3 hydrogens to 2 hydrogens to 1 hydrogen. And remember, it's 1 hydrogen on the carbon. That's what I care about. I care about what carbon's up to. I get that. And eventually you get to the most oxidized form of carbon possible, which is carbon dioxide. Right? So most oxidized. Right? So this would be oxidation. And this way would be reduction. Okay? And what we're going to do is we're going to learn a bunch of different things that'll do this, a bunch of different things that'll do this, so we can selectively choose, I want to turn an alcohol into a carboxylic acid, or I want to turn an alcohol into a ketone or aldehyde, or I want to turn a ketone or aldehyde all the way down to an alkane, right? We want to be able to do any one of these steps. Ideally, we want to be able to do it in one step, but sometimes you have to do it in two. One step is just not an option for some of these scenarios, okay? So that's the goal, because I want to be able to take an alkane, a relatively non-functional and simple molecule, and turn it into something more complex like a carboxylic acid, because there's lots of chemistry you can do with carboxylic acids. And so you can open the door to lots of different types of molecules, right? And the whole point of this class is to make molecules, right? That's what we like to do in organic chemistry. So let's have a list. Let's make a list of oxidizing agents. Right, so all the different things that can oxidize. We already know some of them, right? So we already know things like KMnO4, KMnO4. And we know that the situation that we need to do KMnO4 oxidation can either cold and dilute, where we get a diol, or hot and concentrated, if we want to cleave, right? That's our alkene chemistry. So actually I'll put both scenarios, hot and concentrated, or, I don't know why I'm a fan of the slash. Hot and concentrated, or cold and dilute. And they both have applications depending upon what you want to do. We also know that you can ozonate, do ozonolysis, right? So 1 ozone followed by 2 CH3 dimethyl sulfide, right, to get rid of that extra oxygen. Right? That's also an oxidizing step. We didn't really talk about that too much, but it is absolutely a way you can oxidize things. Some new oxidizing agents that we're going to learn in this chapter will be things like sodium dichromate. This is a really nasty chemical. It's a super strong oxidizing agent. It's terrible for the environment, and usually it's dissolved in concentrated sulfuric acid, so that doesn't really make it too environmentally friendly either, or biologically friendly. We're also going to learn about a chemical called PCC. Talk about that in a little bit. Nitric acid, which typically we use for its acidic properties, having an extra proton, can actually be a decent oxidizing agent itself. Copper oxide, oxidizing agent. Another chrome derivative, which is called dichromate, or Cr2O3. Maybe it's not called, no, dichromate is Cr2O7. Cr2O3. This is called Collins reagent. That's Collins with an O. Collins reagent. Right, so we're going to learn about that one. And then we're going to learn about the Swern oxidation. That's a nice, complex, long oxidation step. Sodium hypochlorite. household bleach is actually a pretty good oxidizing agent. That's actually how it kills things. So, you know, when you wipe your counters down after you cook meat or something and you have bacteria everywhere and you don't want it to get all gross, you wipe it down with bleach. Why do you do that? Because bleach is an oxidizing agent and it goes into the bacteria and it oxidizes all their biological processes and their DNA and their proteins, and it breaks them down, and there's nothing they can do about it, right? Because it's simple oxidative chemistry. You can't stop oxidation, right? Bacteria can evolve to be resistant to antibacterials or antifungals or things like that. But you can't stop simple oxidation. It's just whatever comes in contact with, it oxidizes. We've also seen peroxide used as an oxidizing agent. And there's probably a couple others if we go back and look through our notes. But essentially this is a relatively good list of different reagents that we can use to do these types of transformations, right? Alcohol to acid, or acid to carbon dioxide, or aldehyde down to alkane, to jump all around the oxidation scale. On the reduction side, good news, good news everyone, it's actually a little bit easier. Reducing agents, right? There's only a couple of reducing agents. There's the strongest one that we're going to deal with, which is lithium aluminum hydride, right? So in the case you want to take something that is relatively highly oxidized and you want to reduce it as much as you can, you'll use lithium aluminum hydride. Of course, we've already seen one before in the hydroboration oxidation step, or excuse me, in the oxymercuration demercuration step. And do you remember what the second step of oxymercuration demercuration was? You should. Sodium borohydride. Right. We've also seen to make alkoxides, we can add sodium, or we can add sodium hydride, and those are for the most part, those are the ones we're going to see. Right? There are of course more, but those are the ones we're going to primarily use. So on the reducing side, it's pretty easy. And here's a hint, right? If you're reducing, you're adding hydrogens, they have to come from somewhere. Oh look, they come from your reducing agent. If you're oxidizing, you're likely to be adding oxygen, although technically you don't have to. You can oxidize without adding oxygen. Where do those oxygens come from? They have to come from somewhere, right? So the oxidizing agents have oxygens, not always, but in general, and the reducing agents have hydrogens, not always, but in general, right? So that's a good rule of thumb. So if you see a chemical, you have no idea what it is, you can at least look at what it's made of, right? Oh, it's made of an OCl, or a couple of oxygens. Maybe it's an oxidizing agent, or it'll do oxidation reduction chemistry. So it's at least gives you a chance to stab in the dark. So let's come back to my favorite alcohol, ethanol. And if I add sodium dichromate, right, and this is usually dissolved in sulfuric acid, like I said, this is a very strong oxidizing agent. So it will oxidize two steps. So it'll take this primary alcohol and convert it to an aldehyde, and then it will take the aldehyde and immediately convert it to the next oxidation step up, which is carboxylic acid. So it will convert my ethanol into acetic acid, right? So that's good, because that allows us essentially to do 2 steps worth of oxidation using only one chemical reaction. Cool. What if we didn't want to do that, though? What if we wanted to take our ethanol, I'll redraw it. We want to take our ethanol to which, and we wanted to make the aldehyde, ethanal. We don't know how to name aldehydes yet, so don't worry about it, but it's just called ethanal, al for aldehyde, because we're smart. Turns out there is a way to do this, right? But sodium dichromate cannot do this, right? Even though it does technically 2 steps, it goes alcohol to aldehyde and then aldehyde to carboxylic. You can't stop it halfway through and say, okay, after you get to the aldehyde, stop. I'll dump ice in the reaction to freeze it and cool it off. You can't do that, so it doesn't work, right? So you have to have a different technique. The way you do that in this case, in this oxidation scheme, is to use a compound called PCC, right? PCC stands for pyridinium chlorochromate. Pyridine is this, right? It's a heterocyclic molecule, decent base. We've seen it before, we didn't know it by name. That's pyridine. In organic chemistry, or in chemistry in general, when you tack the suffix ium onto something, what it really means is the positive charge version of. So pyridinium would be the positive charge version of. So if pyridinium is this, chloro is your counter ion, right? So if you ever look at like medicine bottles or sometimes shampoo or toothpaste or other things that we use on a daily basis, it'll say like something 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 hydrochloric acid. What it's really saying is it's the protonated version using HCl to make that happen, right? So we could call this pyridine chromate hydrochloric acid, although it wouldn't be a very official nomenclature scheme. So pyridinium chloro, and chromate is CrO3. So this is where the oxidation power comes from, right? It's the same thing like this, or very similar to it, but it's a slightly weakened or diluted version, right? The presence of this pyridinium kind of tweaks the oxidation reduction chemistry of the chromate, so it can't take the primary alcohol and go all the way to the acetic acid, the carboxylic acid, like dichromate can do, but rather it's weakened, it's hampered, and so it can only take the primary alcohol and stop at the aldehyde. So it stops here. It can't do all that extra stuff. And that's one of the benefits of pyridinium chlorochromate versus sodium dichromate or potassium dichromate. Potassium dichromate is a very strong oxidizing agent. We can also take PCC. We want to do a secondary alcohol, CH3, CHOH, CH3. And here we can turn it into the secondary alcohol, or the ketone, because there's only one level of oxidation. There's only one hydrogen that can be removed from the carbon. So here PCC will do this just fine. Actually, it turns out that you can also use sodium hypochlorite, and you can also use the dichromate, right? Even though dichromate is kind of the super strong oxidizing agent, because there's only one hydrogen to remove, it's kind of all you can do. So in this case, it works out. But ideally, it would be better to use the reagent that's just strong enough to get the job done, and don't go overboard adding the strongest possible thing, because then you get side reactions and side products and all kinds of other weird stuff that you may not necessarily want. Right? It's just bad practice. Okay. So if we want to go backwards, for example, if we take our acetic acid from a little bit earlier, and we want to convert it into an alcohol, turns out we can do that as well. That's a reduction, going from 3 carbon-oxygen bonds to 1 carbon-oxygen bond. And since we're doing 2 steps worth of reduction, from 3 to 2 and 2 to 1, in one chemical reaction, we have to use a really strong reducing agent. And so if we look at our list of reducing agents, and we pick the strongest one, lithium aluminum hydride is the way to go. If we want to go from our carboxylic acid to our aldehyde, so we want to go down in oxidation by 1 level. Okay, so sorry about that, I had to pause the videos, I have to restart. So if we want to take our carboxylic acid and turn it to an aldehyde, it turns out there's no way you can actually do this. You can't take 1 step down, and the reason for that is because aldehydes are more sensitive to oxidation reduction chemistry than carboxylic acids. So anything that you add that is strong enough to reduce an acid will immediately reduce the corresponding aldehyde down to the next level. So how would you do this? Well, it turns out instead of doing it 1 step, you just do it in 2 steps. So what you do is you do LiAlH4, reduce it all the way down to your alcohol, and then you oxidize your alcohol up 1 step, PCC. So you go down 2 and then up 1. Whereas before you could go down 2, that's fine. You just can't go down 1 from this. You can go down 1 from this, but you can't go down 1 from that. Because carboxylic acids play a slightly different game when it comes to bond energetics and oxidation reduction chemistry. So let's take a look at some cool stuff we can do now that we know oxidation reduction chemistry. Let's start with simple alkene, like cyclohexene, and MCPBA, which hopefully you should remember the structure of. Can give me an epoxide. I'm not going to worry about stereochemistry. If I add aqueous acid, I can pop the ring open to give me a trans-diol. Right? And I can oxidize with dichromate now. H2SO4. Right, this is the new thing we're learning, so I could turn this into a diketone. Right? What can I do with diketones? Well, I can do some stuff that we're going to learn later in the chapter, but I don't want to spoil it. Right? If I take, go down to the next page. If I take an alkane, right? And I want to turn into something like that. Doesn't seem obvious how I'm going to do that, right? At least I got the right number of carbons. 3 carbons here, 3 carbons here. One of them is an aldehyde, one of them has chlorine on it. Not particularly obvious how I'm going to make this happen, right? Well, what do we do with alkanes, right? We do the same thing we always do with alkanes. We brominate them so that it's a stereospecific reaction at the most substituted carbon. So the secondary carbon would give me the 2 bromo species, and then we eliminate with a strong base like ethoxide or something, and heat to give me the addition, or the alkene. Oops, in my notes I have the alkene here, so I'm going to draw it there, so keep it the same. And with the alkenes I can do MCPBA to give me the epoxide, and the epoxide I can open up the ring with HCl, right, so that the molecule looks like this. OH goes here, chlorine gets attached there. So now I have all the right atoms on. Now all I have to do is oxidize. How do I oxidize an alcohol to an aldehyde? That's what we just covered. PCC, right? So 1, 2, 3, 4, 5 steps I can get from propane to 2-chloropropanal. But don't worry about that nomenclature. Right, there's other stuff I could do. I could take this and I can use dichromate, Cr2O7, 2 minus. Right, really strong, and I can turn the alcohol into a carboxylic acid. What can I do with carboxylic acids? There's a lot of stuff you can do with carboxylic acids. All of those are chapter 22. So if you want to peek ahead in the book just to see what you can do, go ahead. But carboxylic acids can do essentially like 3 chapters worth of stuff. There's a whole 2 or 3 chapters based on carboxylic acids and their derivatives chemistry in Wade 7th edition textbook. So, all right. So now we know how to make stuff like this, aldehydes and ketones. What are we going to do with aldehydes and ketones? Well, this is where we get into our next topic, which is crucially important both in organic chemistry and for my class and for the ACS exam, because it's a very popular topic. And that would be Grignard. Okay, so this is Victor Grignard, a French chemist from the 1900s. It's pronounced grin, like you're smiling, like the devil likes to grin, and yard, like Scotland Yard, right? So it looks funny because he's a Frenchie, but Grignard, that's how it's pronounced, right? A Grignard takes an alkyl halide, and you add magnesium metal to it, right? It doesn't seem to make any sense why you would add magnesium metal, and you have to specifically do this in an aprotic solvent. So one of the best solvents to do this in is diethyl ether, right? Polar aprotic is the way to go. What this gives you is the magnesium inserting itself in between the carbon and the halogen, and so you get a compound that looks like this. This thing is called the Grignard reagent. It's highly reactive, and it has some special properties. The Grignard reagent is essentially, or at least you can think of it, as an equilibrium between a carbanion and the magnesium halogen cation. Carbanions, we know, are really good bases, but more importantly, they can be nucleophiles. And so if I take a squiggly line, I'm going to do it over here. Hope you guys don't mind that. If I take a I'll draw it this way. Sorry. Take my Grignard and I add carbonyl, like a ketone or an aldehyde, which we just learned how to make 10 seconds ago. The Grignard can act as a nucleophile and attack the carbonyl. What it gives me then is the carbon-carbon bond, a new carbon-carbon bond, and specifically it's that bond right there. Right? That's really important because so far in organic chemistry we've only learned one way to make carbon-carbon bonds. Do you remember what that way is? Pause the video and try and think for a second. Hopefully after unpausing the video you remember that the way to make carbon-carbon bonds is through the acetylide ion, again using it as a nucleophile. Okay, if we add a little bit of acid or a little bit of water, what have we just made? What type of functional group is this? It's an alcohol. Right, so not only is this a way to make alcohols, but it's also a way to make new carbon-carbon bonds. So there's a lot of functionality you can get Grignard chemistry. Really helpful stuff. So I could take something as an example. I could take bromobenzene, and I could add my Mg. And this is magnesium metal, so it has zero charge, right? It's not magnesium ion. And diethyl ether, so I get my phenyl magnesium bromide, which is what this is called. This will act as a nucleophile. I can attack some target. Suppose I attack the product of my previous synthesis, ethanal. Then I will get CH3, C. So these electrons will go here, and those will go up. These becomes O minus. H is still there. And what bond have I made? I made this bond right here. So this carbon is now bonded to this carbon. So I get this. I could leave it like that, and technically it would, MgBr would hang out because it's positively charged next to that guy. That becomes a solid, falls out of solution. But I could leave it like that if I wanted, but I can just add water or aqueous acid. It's a little bit easier to make it, to acidify it, than it is to use water. To get the alcohol, right? And we know what we can do with alcohols. We could oxidize them, right? So I could oxidize this to a ketone and do it again if I wanted to, right? So think about something like this. I did my favorite cyclohexane, and I want you to make benzoic acid hexane. Alright, so the first thing we should recognize if we want to do a synthesis like that is that somewhere along the line we're going to have to add some carbons, right? Well, specifically we're going to have to add one carbon, right? So there's a couple different approaches we can take with this, but the way I'm going to do it is I'm going to brominate my guy first, because that's what I like to do. So bromine and Hv, do the radical mechanism. Hopefully you remember the radical mechanism from chapter 4. And then I can turn this into a Grignard by adding magnesium and ether. Now I have a nucleophile. Okay, I want to attack a particular target, right? So I want to add a carbon because I want to make a carbon-carbon bond, specifically this bond right here. And so there's a couple ways I could do this. I could pick first to add this guy. So that would give me this. Then I have to add water or acid. Doesn't matter. So that would give me that. I'm just protonating this alkoxide. And how do I oxidize a primary alcohol to a carboxylic acid? We learned this earlier. This is an oxidation step. Sodium dichromate will work just fine, nice and strong, because we want to do 2 steps worth of oxidation at once, right? Another way I could have done it is I could have taken this compound and I could have added carbon dioxide. So you can actually literally take carbon dioxide gas, bubble it through the liquid solution containing your Grignard, and you get the carboxylate anion. And then you just have to add a little bit of acid. Water's not good enough in this case. A little bit of acid to protonate it, and you get your product. Right? So 2 approaches, either one will work. Attack the ketone, attack carboxylic acid. In one case, I'm just adding, I'm adding the carbon-carbon bond, then I'm oxidizing, versus I'm adding something that has already been oxidized, and then I'm just protonating. Okay. So let's see what else. We can make, this is, because we attacked a carbon that was just one carbon by itself, we end up with a primary alcohol. If we attacked other carbons, it would be a carbon that gives us secondary or tertiary alcohols. So if I wanted to make a secondary alcohol, I'll take a Grignard, maybe something like this, and I have to attack something that has 1 carbon. So when it attacks, goes up, what is the product? This is the original, that's the bond that was made. It's bonded to this carbon, which has an O, an H, and a C, an O, C, and then followed by water workup. Get that secondary alcohol. Right? If I want to make a tertiary alcohol, take my Grignard, doesn't matter which one it is, and I add a ketone. Why do I have to add a ketone? Because this carbon that is going to be bonded, that's going to get attacked, has 2 carbons bonded to it already. This carbon will be the third, and so the result will be whatever my R group was. This is a tertiary alkoxide, which followed by water workup becomes a tertiary alcohol. Okay. So we can pick what type of alcohol we want to make using Grignard chemistry simply based on what is the target that we pick: an aldehyde, a ketone, a carboxylic acid, or a carbon dioxide, or etc., etc. All right. Let's see. What else? One of the things I've been saying with Grignard is that you have to have this. Why do you have to have this? Why can't you use water or ethanol or something like that? Let's take a look. Suppose I did this. Suppose, where am I at? Use this guy as an example. Suppose I took this bromine and I said I'm going to add magnesium metal and I'm going to add diethyl ether, but I was lazy when I cleaned my glassware. I didn't really pay attention. I didn't clean it very dry. I didn't put it in the oven. So there's some water hanging around. What's going to happen? Well, if you were lucky enough to make the Grignard, right, we said that Grignards are essentially equilibrium between the carbanion and the anion. What is this going to do in the presence of water? Pause the video and take a minute to figure it out. After pausing, you should have said, well, we have been using these as a nucleophile, but they're also really strong bases. And so if we accidentally leave water or other ionizable protons around, we destroy our Grignard and we make an alkane. So really, I mean, this is a very roundabout and inefficient way to turn an alkyl halide into an alkene. Right? So if I were to accidentally do some chemistry like this, and I just dump in my electrophile, this type acetone, and I used diethyl ether, but again, I was lazy and didn't clean my glassware, or I tried to do not in 2 steps, but I tried to do it in 1 step, or instead of adding first the electrophile and then the acid workup, I just dump it all at once because I'm in a hurry. What will my product be? This. Because the acid-base chemistry here will happen thousands of times faster than the nucleophilic chemistry here. Now, will you get a tiny, tiny, tiny amount of the substituted product where the nucleophilic chemistry happens? Yeah, maybe a little bit, but for the most part, you're only going to get reasonable amounts of the acid-base product, which is just the alkane. Okay. What about things that have leaving groups, or things that are not just aldehydes and ketones, like an ester? What if I took methyl magnesium bromide as my Grignard, and I reacted it with an ester, right? So you remember an ester functional group looks like this, followed by aqueous workup. Go ahead and pause the video and see if you can figure out what the product is and what the mechanism is. Okay, after pausing, hopefully you remember that this is a nucleophile, so minus and plus. The electrons will attack here. Electrons go up. That will give me something that looks like this. And the new carbon-carbon that's been bond that has been formed is that. But this, as it turns out, has a built-in leaving group. Esters have built-in leaving groups. So the electrons will push back down and kick out the leaving group. In this case, the leaving group is an alkoxide. Oops. And I will get a ketone as a functional group. Well, what do Grignards do in the presence of ketones? They do the same thing we've been talking about. So the Grignard, or another molecule of the Grignard, will be a nucleophile in attack, and so your final product will be not the monosubstituted product, followed by acid workup, but the di-substituted. That's supposed to be a methyl. CH3. There we go. Because esters will react with two equivalents of the Grignard, one equivalent here and one equivalent here. And that's because they have this built-in leaving group. So based on that, can you predict what the product would be if I took the same Grignard? I'll use magnesium chloride, so it's slightly different. And I'll do H3C. And an acyl halide. Go ahead and pause the video and see what you get. Hopefully you know that the answer is T-butanol. I'm not going to draw the mechanism for this one. I'm going to leave it for you guys to try and figure out. And you should be able to do that. Okay, so now there's all kinds of games that we can play. So I'll give you a quick example of games that we can play with, now that we know Grignard chemistry. I can start with something, a simple alkane, like ethane, and I can end up with things like cis and trans butene. Or I can end up with alkoxides, right? I know how now to turn this into these guys. Or I could turn it into this, right? Plenty of different ways. Doesn't seem obvious on the face of it, but now that we know how to link carbons together, we say, oh, I have 2 carbons, I have 3 carbons, so I need to make a carbon-carbon bond. Oh, I know how to do that. Grignard chemistry. I have an oxygen. I don't have an oxygen. Oh, I know how to oxidize stuff. I know how to make alcohols. I need an alkene to do that, etc., etc., right? So I can brominate and then eliminate. Same trend we've been seeing for many, many chapters now. Oops, I added a carbon here on accident. Where am I at? There we go. And then I can epoxidate. Does this look similar to what we did a couple syntheses ago? Hopefully it should. Just getting this out of the way. If I epoxidate, that would give me that. And now is where I'm going to make my carbon-carbon bond, because Grignards, CH3 MgBr, followed by aqueous workup, or acid workup. Right? Grignards can attack epoxides just like they attacked carbonyls. And so to do that, that would make my carbon-carbon bond and give me the alcohol. Right? So this would be the new carbon that was added. These are the original. So if it attacks here, actually I drew these arrows in a bad place to draw here. So it goes that way. So that way this oxygen is that oxygen, and this carbon is this carbon, and this carbon is this carbon. Right? How do I deprotonate an alcohol? I can use a strong base, or I can use sodium hydride, right, to off-gas the hydrogen to get the alkoxide. I could take that alcohol and I can eliminate it. I know how to do elimination of alcohols. That's just that. I can put the alcohol back on if I wanted, doing the same thing. But now it's in Markovnikov edition, so I'd get that. So I selectively go from primary alcohol to secondary alcohol. And I know how to oxidize a secondary alcohol to a ketone, right? There's a couple different ways we know how to do that. PCC, dichromate, sodium hypochlorite, etc. Here I have 3 carbons. If I want to turn it into 4, somewhere along the line I'm going to have to add a carbon. So I need to make a carbon-carbon bond. So what do I need to do? Oh, Grignard. So I need to turn the Grignard into a target. So MCPB. I'm going to change it. I'm going to do MMPP. Same thing, it just gives me the epoxide. And then once I epoxidate, I can use my CH3MgBr again, followed by aqueous acid workup. And I need a little bit more space to draw. Right. After I do that, the Grignard will attack the more available position, because it's a very strong nucleophile, to give me this. and then I can dehydrate with the same reaction we're doing to give you cis and trans, right? And we could do stuff with this, and we can continue to play this game, oxidation reduction, over and over again. What we're going to see next chapter, in chapter 11, which I'm about to cover now, is that we can reduce alcohols directly to alkanes. And that's a handy trick to be able to do, just in case you want to do that. Right? It's nice to be able to get rid of stuff. It's just nice to have control, right? To be able to decide what you want to do, where you want to do it, and what you want the stereochemistry to be. Right? So this is a type of scheme I would like to ask on exams. So be familiar with that idea. All right, last topic of chapter 10. Thiols. All right, a thiol is essentially a functional group that looks like this. They do the same chemistry that OHs do, although they're slightly better nucleophiles because they're more polarizable. Right? You can still add sodium hydride to make the thiolide, I think it's called. I have to look up the exact name of this, but the sulfur with the negative charge. And sulfur with negative charge is actually good ethanough to attack alkyl halides. Oxygen can do this too, but not as well. You have to change the conditions a little bit. And so you can make thioethers, and then sodium halide as your counterion, right? And they're really common in biochemistry, which is really the only reason I'm even mentioning this, right? So a lot of you might go on to take bio-based classes. You'll learn about the amino acids and all those gooey things in biology. It turns out that there are some very important amino acids in many living creatures, if not all, that use thiols to hold their proteins together. And, you know, proteins that stay together and do what you want them to do, I guess could be a good thing. Makes things stay alive. So, take two amino acids, like cysteine, and we can oxidize them, right? Or the body will oxidize them. Of course, you can reduce them too. And you remove these two hydrogens in the oxidation step, and you can form what's called what in biology is called a disulfide bond. I guess we would call it a persulfate, or a persulfide bond, because it's got two sulfurs in it. But sulfur-sulfur linkage. And it's really handy for biology to do this because the energetics of making and breaking this sulfur-sulfur bond isn't that difficult, right? We already know that oxygen-oxygen single bonds are garbage, right? We're not going to do that in a biological system. They break homolytically, they generate radicals, they're uncontrollable, bad news, right? Remember the peroxides? They break like that. That's bad. We don't want to do that. Sulfur bonds are much more stable. They hang out like this. They don't mind. And so biology will use this disulfide bond right here to hold proteins together in their three-dimensional structure. And if we wanted, we could name thiols. We essentially just add the word thiol to the name of the alkane, to the alkane name. It's the lazy man's way. I guess IUPAC forgot about thiols, and at the end they're like, oh crap, we forgot, we got to name those too. Well, just stick on the word thiol, right? So if I had this thiol, 3 carbons is propane. So the IUPAC name is literally propane thiol, one word. The common system, which you will also see, is, well, you won't see from me, but you'll see if you look in literature, is to say the name of the alkyl substituent, 3 carbons, which would be propyl, and then instead of saying thiol, you use this word mercaptan, which I think sounds cooler, right? Mercaptan, because thiols, back when they were first discovered, people didn't know what the hell they were, but they did know that often when they found thiols, they were found with mercury. That's where the mer comes from. So they often captured mercury, and so they were just known as mercury-capturing compounds, or mercury-capturing molecules. So no one really knew what they were, so they, through the Latin, were converted to mercaptan, and then, you know, organic chemists started using the phrase mercaptan, and so it just stuck. So this is the IUPAC name. And this is the common name. I don't really care about the common names, but they are still very common, right? Especially if you talk to older gentlemen in the organic chemistry, or older ladies. They know these mercaptans. Here, right, this would be a pentyl group, so it would be pentane, pentane, And what do we have? At the 3 position we have our OH, or our SH, so we tack on thiol, pentane 3-thiol. It's quite stupid. Alright, so that's all it is. I'm not going to get all into depth with thiol nomenclature. Right? Oh, here in my notes I have it from Latin. Mercurium captans, which stands for capturing mercury. Neat. Okay, so in class I showed you the Swern oxidation, and I'm not going to draw it out here simply because I'm tired and lazy. And I'm not going to expect you to know it. Right? So just to be clear, you do not need to know the Swern oxidation, although I would love it if you did. The Swern oxidation is a specific way to make an aldehyde from a carboxylic acid. So I will just give you a quick summary of Swern. Right. Swern takes a primary alcohol, right, akin to the way PCC works, although in this case it takes dimethyl sulfide, or DMSO, dimethyl sulfoxide, and oxalyl chloride, which is this crazy high energy molecule, and the presence of an organic solvent and an organic base like triethylamine, which smells absolutely freaking disgusting, by the way. My company used to make it. And we get our aldehyde, so we turn this into this. That's the important part. And all the leftovers are this, 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 and that. I actually get 2 of those. Right, so there's lots of stuff. But the important part is alcohol gets turned into aldehyde. Right? So, simple question you might see. I don't know if ACS talks about Swern, honestly. I don't remember. I don't think so. It's just an alternative to PCC. Right? So, I believe PCC is usually done under acidic conditions. So, if you want to have a more neutral condition-based oxidation, you can do that. So, take my favorite alcohol, ethanol. Instead of using PCC, you can just be lazy and write Swern and get ethanal, the aldehyde. Alright, that's the end of Chapter 10. I will make one more video for Chapter 11. It will be short. I'll make it relatively soon. And it's only a couple pages worth of notes. It's just games and tricks and reactions you can play with alcohol. So good luck studying, and I will see you guys next week.